All right, let's talk about one of the most incredible moments in all of physics. Back in 1865, a Scottish physicist, James Clerk Maxwell, puts out this set of equations that, well, they didn't just describe the world, they literally rewrote reality. He took these three things that everyone thought were totally separate, electricity, magnetism, and even light, and he just wove them together into one beautiful, elegant theory. He showed us that they weren't just kind of related. No, they were all just different faces of the exact same thing. So how on earth did he do it? Let's find out.
It's really hard to overstate just how huge this was. I mean, the blueprint for pretty much everything we rely on today, your smartphone, your Wi-Fi, all of our modern communication, it was all written down way back in 1865. Every single time you connect to a network, listen to the radio, or honestly just look at the world around you, you're living inside the consequences of these equations. They are the absolute bedrock of our modern world. And that really gets at the scale of what he pulled off. I mean, think about it. Before Maxwell, what did we have? Basically a jumble of disconnected lab results. It was messy. But after him, boom, we had a unified fields theory, a complete, total description of electromagnetism that, by the way, paved the road for guys like Einstein and the absolute upheaval of 20th century physics.
So, here they are, in all their glory. These four equations are what we're going to dive into and really unpack. And what's wild is that this super clean, compact form, well, this isn't exactly what Maxwell wrote down. His original theory was a beast. We're talking over 20 different equations. It was actually another brilliant mind, Oliver Heaviside, who came along later and boiled it all down into this powerful, elegant vector format that we still use today.
Okay, so to really get what Maxwell did, we first need to rewind a bit. We gotta understand how physicists saw the world before him. And that world was all about static fields, fields that don't change over time. The first two equations on our list, they nail this static world perfectly. Now, if you look at Gauss's two laws right next to each other, you see something really interesting, a deep difference between electricity and magnetism. So Gauss's law for electricity tells us that electric fields start on positive charges and end on negative ones. Think of them like sources and sinks. You can have a lonely positive charge all by itself, no problem. But then you look at Gauss's law for magnetism, and it says something completely different. It says magnetic field lines always form closed loops. They don't start or end anywhere. And what does that mean? It means you can never ever find a magnetic north pole all by itself, or a south pole, no magnetic monopoles. So yeah, in this static picture, electricity and magnetism look like two very different animals.
So yeah, that static world was pretty well figured out.
But this is where the story gets really good, the real magic. The key that unlocked this whole unification thing was when physicists started looking at fields that change over time. This dynamic dance is where electricity and magnetism finally showed their hand and revealed just how connected they really are. Now, Maxwell didn't just pull this out of thin air, right? He was standing on the shoulders of giants. So back in the 1820s, you had Oersted and Ampere figuring out that electric currents, moving charges, they create magnetic fields. Okay, cool. Then, in 1831, the legendary Michael Faraday shows that the reverse is true too. A changing magnetic field can create an electric current. That was the first big clue of a deeper link. Maxwell's genius was taking all these clues, all these experimental facts, and weaving them into one complete, rock-solid mathematical theory, a theory that decades later Heinrich Hertz would prove experimentally. All right, so here's the core of Maxwell's big idea. He had Faraday's law on one hand, a changing magnetic field makes an electric field, and on the other hand, he had Ampere's law, an electric current makes a magnetic field. But he saw a flaw, a big one. Ampere's law just didn't work for everything. It was fine for steady currents, but for something like a charging capacitor, where charge is building up, the whole thing just fell apart. It actually violated the conservation of charge, which is a huge no-no in physics. So what did he do? He came up with this brilliant, radical idea, a new kind of current he called the displacement current. And adding this one little term didn't just fix the math, oh no. It revealed this beautiful, hidden symmetry in nature. A changing electric field can also create a magnetic field. It was the perfect mirror to Faraday's discovery. And this idea, this displacement current, is really the final piece of the puzzle. It's not a current like we normally think of it, with electrons flowing through a wire. Not at all. It's really the effect of a changing electric field. It's the missing link that says a changing E field can create a B field even in empty space, where there are no charges to move around. And that was the final chain that bound electricity and magnetism together forever. Okay, so to really truly appreciate how beautiful these equations are, it helps to speak their language a little bit. So we're going to take a quick detour and talk about the math of fields, specifically the little tools or operators that tell us what's happening at a single point. You'll see Maxwell's equations written in two different forms, and they're totally equivalent. There's the integral form, which is kind of like the big picture view. It tells you about the overall field in a whole region based on what's happening at its edges. Then there's the differential form, the one we're looking at, which is more like the local detail view. It tells you what the field is doing at one tiny infinitesimal point. They both describe the exact same physics. It's just a zoom in versus zoom out perspective. So this differential form uses two key ideas, divergence and curl. Let's start with divergence. Think of it as measuring the sourciness of a field. A sprinkler head? That's positive divergence. Water is flowing out, spreading from a point. A drain in your sink? That's negative divergence. Easy enough, right? Then there's curl. This measures the whirlpoolness of a field, how much it's rotating. The classic analogy is to imagine putting a tiny little paddle wheel in a river. If the water makes it spin, then the river has curl at that spot. So, how do we know for sure that the big picture integral view and the local detailed differential view are telling the same story? Well, that's where really powerful math theorems like Stokes' theorem come in. What it shows, basically, is that if you add up all the tiny little curls, all the little whirlpools at every single point inside a region, the total result is exactly equal to the overall circulation around the outside edge. The local stuff perfectly predicts the global stuff. It's this deep mathematical link that proves the two forms of the equations are just two sides of the same coin. All right, so now Maxwell has his complete, symmetrical, beautiful set of equations. And with them, he's about to make one of the most breathtaking predictions in the entire history of science. He's about to tell us what light is. And he did it by asking a really simple but profound question. Think about it. We know a changing magnetic field creates an electric field. And now, thanks to him, we know a changing electric field creates a magnetic field. So, what happens if you just let this process run free in empty space, far away from any charges or currents? Well, what you get is this incredible feedback loop. A changing B field makes a curling E field. But now that E field is changing, so it makes a new curling B field, which is also changing, so it makes another E field. And on and on and on. They create each other, leapfrogging through space in this beautiful, self-propagating dance. It's a wave. So Maxwell sits down and does the math. He combines his two dynamic equations, and what pops out is a classic wave equation. But here's the mind-blowing part. The equation predicted the speed of this wave. And that speed wasn't just some random number. It was locked in by two fundamental constants of nature, epsilon naught, which measures how electric fields travel through a vacuum, and mu naught, which does the same for magnetic fields. And the craziest thing is, physicists already knew these numbers from simple, boring, tabletop experiments with batteries and magnets. So he takes the known values for these two constants, plugs them into his new equation, runs the calculation, and out pops a number, roughly 300 million meters per second. And to every single physicist alive at that time, that number was instantly, shockingly familiar. It was the speed of light. This has to be one of the greatest eureka moments in all of science. Maxwell realized the speed of his theoretical wave, born from electricity and magnetism, was the exact same as the speed of light. The conclusion was just inescapable. Light wasn't its own separate thing. Light is an electromagnetic wave. As he put it himself, this velocity is so nearly that of light that it seems we have strong reason to conclude that light itself is an electromagnetic disturbance in the form of waves. Just like that, he unified electricity, magnetism, and all of optics into one. So yeah, Maxwell's equations are the absolute foundation of what we call classical electrodynamics. But the story doesn't end there. Their influence goes even deeper, giving us the tools to model the real, messy world, and even acting as a bridge to modern physics. You know, in practice, physicists and engineers actually use two different flavors of these equations. The microscopic ones we've been talking about are the most fundamental. They describe what's happening in a perfect vacuum, down to every last little charge. But trying to use those inside, say, a chunk of iron, it would be a nightmare. So for that, we use the macroscopic equations. They cleverly average out all the tiny atomic details and use a couple of helper fields, D and H, to handle how materials respond. It's just a way more practical approach for building real-world stuff. Now, as incredible as they are, we now know that Maxwell's equations aren't the final word. They're what we call a classical theory. The deeper, more fundamental story is called quantum electrodynamics, or QED, which brings quantum mechanics into the picture. But, and this is a huge but, that doesn't make Maxwell's equations wrong. Not at all. They are the classical limit of QED, and they are so ridiculously accurate that they work perfectly for pretty much anything we want to do, from designing a radio to guiding a probe to Mars.
When you think about it, what Maxwell did was more than just physics. It was a giant leap in our human quest to find simple, beautiful principles that governed the whole universe. His unification paved the way for others, like the electroweak theory. And that same quest, that same dream he championed, it continues right now, as physicists hunt for a grand unified theory that could bring in the strong nuclear force, and maybe even gravity itself, into one final theory of everything. His work isn't just history, it's the inspiration for the future.